Hi, everyone. Welcome to the talk about building a Kubernetes operator for a distributed database at the very first DevXConf. Exciting. My name is Natalie Pistunovich. I'm a developer advocate lead at Aerospike, a Google developer expert for Go, an OpenAI developer ambassador, and I organize the Berlin user groups for Go and women tech makers, and the conferences GopherCon Europe, Cloud9, Hey, and besides Berlin. You're welcome to follow me on Twitter at Natalie Piss. And if you learn anything new or interesting from this talk, which I hope you do, please tweet and tag me, but also tag the conference at DevXConf. So what's on our agenda today? We'll talk what are Kubernetes operators. We'll talk about that. Then we'll talk a little bit about what is Aerospike, so we can understand better the high-level design of it, which I'll introduce you to. And we'll focus on some of the engineering challenges we faced when we developed ours. So what is a Kubernetes operator? Kubernetes is designed for automation. Matter of fact, it offers it out of the box, and you can use it to automate deploying and running workloads. And also how Kubernetes does that is something you can automate. The core of the Kubernetes control plane is the API server. It exposes an HTTP API that lets users, different parts of the cluster, and the external components communicate with each other. Operators are clients of the Kubernetes API. They act as controllers for a custom resource. In Kubernetes, controllers are control loops that watch the state of your cluster, and then they make or request a change where needed with the purpose of moving the current cluster state closer to the desired state. A controller tracks at least one Kubernetes resource type. In our example, operator is a controller for a custom resource. A custom resource is an object that extends the Kubernetes API or allows you to introduce your API into the project or a cluster. A CRD, a custom resource definition, is a file that defines your own object, and it lets the API server handle the entire lifecycle. For example, Aerospike is a database and it's a custom resource. Our engineers built an operator for it because it's not part of the Kubernetes ecosystem. The operator pattern is used for automating repeatable tasks, and it combines the custom resources and the custom controllers. Basically, it's meant to take the human out of the equation because it's boring. And when you do boring things, you make mistakes. Was that confusing? In case you didn't write your own operator by now or didn't dive so much into the operator that you're using, maybe that was a little bit confusing, so one more time for the people in the back. We start with a user that tells that it wants to do things, so it sends a command to the Kubernetes cluster. The API server exposes this HTTP API that, as we said, it lets the end users, the different parts of the cluster, and the external components communicate with each other. Kubernetes creates pods to host the application instances, and each pod is tied to a node. A cluster is a set of node machines or worker machines that are called nodes, and they run containerized apps. Every cluster has at least one worker node, and let's say in our example, we have n pods tied to n nodes. They're created by the deployment object. Deployments are used for stateless applications, like web servers. Pods that are deployed by a deployment are identical and interchangeable, and they're created in a random order with random hashes in their pod names. On the other hand, a stateful set is used for stateful application, as the name might suggest. When dealing with databases, you definitely want to have the stateful set because you want to persist and store the data. Pods that are deployed by stateful set are not identical. They each have their own identity, and that's kept between restarts, and each can be addressed individually. An abstract way to expose an application running on a set of pods as a network service is our next object. And the last one is config map. That's an API object that is used to store a non-confidential data in key value pairs. Pods can consume these config maps as environment variables, as command line arguments, or as configuration files in a volume. A config map allows you to decouple environment-specific configuration from your container image, so the application is pretty portable. Many more objects in this ecosystem, but this is what we need for our example. Of course, we also need a controller. As we said, this is making sure that if there is a difference between the current state and the desired state of the cluster, this will act to make sure that it's getting towards the desired state. And a controller tracks at least one resource type. Then there is a custom resource, for example, our database. And this one is controlled by an operator. Both concepts of controller and operator, they represent a pattern. It does not involve a language-specific implementation or framework. So if you want to write a controller or an operator, you can do it in any language of your choice. You just need to follow the convention. So to summarize this in a writing form, you can say that a Kubernetes operator minimizes manual deploying and lifecycle management. You can expect it to do things like complex resource management, scale the cluster up and down, and do things like version upgrade and downgrade. You can use it for configuration management and for monitoring. As we said, take out the human from the equation to minimize mistakes and automate the boring things. So what will our operator manage? Let's talk a little bit about Aerospike. It's a NoSQL database, and it implements a hybrid memory architecture where the index is purely in memory, so not persisted, and the data is stored only on a persisted storage, SSD for example, and it reads directly from the disk. The disk I/O is not required to access the index, and this enables a predictable performance. The SLAs with the clients are pretty strict. Petabytes of data in sub-milliseconds. You can have strong consistency, which you probably heard of from the CAP theorem. And there is transactional guarantees. So the database transactions provide asset guarantees if needed. This is why huge clients, for example, banks or others from the finance industry and other industries are using it. Other features that will be relevant for our operator, and I want to mention, is rack management. So this allows you to store different replicas of records on different hardware failure groups. You do this for resilience. And multi-cluster cross data center replication setup. Multi-site is a setup where the nodes comprising a single cluster are distributed across sites. It can be a physical rack in a data center, an entire data center, an availability zone in a cloud region, or others. Basically, the cluster is stretched across regions, cloud providers, and it expands horizontally. This uses synchronous replication to deliver a global distributed transaction capability, and the update speed is only limited by the speed of light. It can also go asynchronous, and in that case, we'll use the cross data center replication setup that uses the asynchronous replication to connect to clusters that are located at different geographically distributed sites. It can extend the data infrastructure to any number of clusters easily. So, the Aerospike Kubernetes operator. The high-level design of it, it's driven by a single custom resource, CR, and it conforms with the operator custom resource definition, CRD. The cluster specs cover things like the size, so number of nodes per cluster, and the resource allocation request, for example, CPU per node. and it handles the complete Aerospike configurations. So yes, it has the YAML version of the Aerospike server configuration, and it converts from the YAML-based ones to the Aerospike language configuration. It also handles security configuration, TLS, and user management, and so on. And we discussed a little bit the features of Aerospike, and those introduce some special considerations for things that it should do. So you can, of course, expect it to deploy the database clusters, and it manages all the things. Lifecycle management, for example, the database cluster scale up and down, server version upgrade and downgrade, the Aerospike configuration management, the rack awareness management, the cluster access control management, and the setup that you need for the multi-cluster XDR. And as we said, it spans across many different types of servers in many different geographical zones and hardware or cloud or multi-cloud. So lots of specifics, and it's really great to automate. And it also handles the monitoring. So when building it, we faced all sorts of engineering challenges, and I'll tell you about 3 of them. First one being the persistent data. So each pod has a dedicated storage. And as we said, it must be persistent because we are talking about a database here. So the logic is that first time you're assigned a volume, you need to wipe it. Just like with computer memory, you cannot assume that the storage is going to be empty or full of nonsense. But if it's a volume of a restarting pod, you don't want to wipe it. When you change the configuration, the pod restarts. So of course you want to keep using the data. Or if something went wrong and the pod has to restart, you still want to be able to use it. So don't touch that data. But there is no Kubernetes way of telling if it's a restarted pod or a new pod, because you probably updated the image and, well, all metrics are set to 0. What are you going to do? A flag. Flag is the solution. We add a flag using init containers. These are the containers that you run before your containers run, and that's how you init the devices. This is where you do wipe the data, and in order not to wipe the data twice, on the restart, for example, the operator makes for each resource a CR, in which it creates a singleton instance upon initialization. Basically, when you wipe the data for the first time, you add a flag. And then if you do a pod restart, you're just going to look in the config and you're going to see whether the flag already exists there. And if it does exist there, you know not to wipe the data. The next challenge is what happens during a rolling update. So let's say that something happened and the operator started the rolling update. In the middle, you realize this is not what you want to do and you need to abort. So you see this is printed on the screen. Update on node 1, complete. Update on node 2, complete. Same for node 3. Then the realization to abort hits you. What happens? What are you going to see in update on node? It sounds pretty straightforward, right? You wanted to stop everything and just reapply the old version to nodes 1 to 3. But if you send to the operator the command, update all 10 nodes, it makes sense that it will first complete 4, 5, 6, 7, 8, 9, 10, and then get the revert command. And in specific use cases, when you have a lot of traffic or when things can go wrong from the new setup, you want it to stop immediately. You cannot take those few additional changes. So that's why we implemented the setup in the way that after every operation, it requeues the reconciliation request. Basically, the operator is asking the API, now what? This way, it completed updating node number 3 to the new version. And the next step would be, what do I do now? And the API says, apply old version to nodes 1 to 3. So instead of saying updating new version on node 4, it will say updating version on node 1. Hooray! This is what you wanted it to do. And to make things even more efficient, the operator requests delay in the response. For example, let's say the node is in the middle of a migration and it knows that it will take some time. Then the operator tells the API, now what? But don't respond just yet. Hold on a few seconds, and this long until I finish the migration, because I will not be able to abort the migration for this one specific node in the middle. And your decision might change by the time you respond. So it tells the operator tells the API, wait a few seconds and then respond. And then when the migration of the current node is done, the operator gets the most up-to-date response. And this sounds very trivial. Probably when you dive into the problem long enough and when you see how different operators are doing this, this very obvious solution looks slightly less obvious and more of a aha in a type of a hindsight setup. The third challenge is what happens when you go to a really, really large scale. So cloud is great for prototyping, and as you go bigger, it gets a little pricey. And we have customers with 500 billion objects. To give you an understanding of what is 500 billion, imagine that $1 buys you 3.5 objects. Now, this is a little bit of a funny thing to say because an object is kind of an entry in the database and $1 won't buy you 3.5 entries, but let's say for our understanding, then 500 billion is how much Jeff Bezos can afford. This is a client of ours, and some clients have requirements for petabytes of traffic and all handled in sub-milliseconds. So the scale can get really big. Then there's a problem that the cloud is not homogeneous. There is a promise of a minimum CPU, but it doesn't mean that all the CPUs are like that. It means that the minimal CPU is like this, but it can be that the other CPU is more than that. Aerospike, because of its architecture, is disk heavy. Sharing the I/O means that you definitely get a slice, but it's hard to cap the size of it. This can mean that the machine might respond slowly to messages. In a distributed database, there are a lot of messages going on. There's a synchronization that is going on all the time. You want to make sure that all the copies know which one is the most up-to-date one. And well, you want communication with endpoints like the heartbeat. Then there is the networking. And when the network is not private, you get a slice of it, but you have to share it, right? And if you have noisy neighbors, they can drive your performance down. Not to talk about the cascading effect of any of these interruptions. That's really hard to predict. So as the slide says, this is a situation that once you arrive to it, an operator alone will not solve this. The solution that some of our clients are doing is private cloud. When you reach a really, really, really large scale, get the whole host and split the resources internally. And of course, budget for some overcapacity. When your client is Snap, for example, in their scale, you do want to read from the client, not from the master. So be aware, max your communication to a local one because latency matters a lot at this scale. The Kubernetes operator is great in this setup. Think about this. Kubernetes started inside Google in their private cloud. So of course, the operator will work great in such a setup as well. And to recap, we talked about the Kubernetes operators and how they control the custom resources. And we understood a little bit the architecture and how those things work with each other. And then I told you a little bit about the challenges we had building the operator for a distributed database and the takeaways that you can take home. Keep the data upon a pod restart. because you are using a database. Be able to revert a rolling update immediately. Don't wait until the update is run on all the nodes. Have an option to stop it in the middle. And be aware that when you go on a really, really large scale, you might have new problems and the solution might be bigger. And of course, automate, automate, automate. The source code is, of course, open source, available on GitHub. You're very welcome to read, learn, contribute. I'm happy to chat about this very much. And again, if you learned anything interesting, please tweet at the conference. Please tweet at me. And thank you very much.